Aspetta, questo è attacco.
Un minuto.
Sì.
Siamo puntuali.
Si chiama Reveal.js.
Ah, sì, sì, sì.
È un po' un casino.
Credo che sia quello che fa.
Un po' un casino, te lo dico. Perché io faccio un sacco di diagrammi, no? E questo è JAS, perciò ho tutti i metti FSVG.
Beh, sì.
Non puoi disegnare. Mi piace disegnare.
Cosa
Allora io ho disegnato tutto e poi ho esportato in SVG e ho buttato.
Okay, welcome back everybody. We are second talk of this morning. Speaker is Daniel Pyrathon, a friend of the community, a nice guy who's doing some work with machine learning, and he's going to talk about interesting stuff. So welcome him. Thank you.
Hi, my name is Daniel Pyrathon, and today I'll be presenting machine learning as a service. Okay, mainly with using two really good libraries. One is NLTK, and the other one is ZeroMQ. Okay, so first of all, a little bit about me. Okay, so I was born in Rome, so not too far away from here. Okay, I have just graduated, and yes, thank you. And that is me with my crocodile suit. And currently I'm working on Django as part of Google Summer of Code. So the next 3 months I'll be working on refactoring meta classes. And actually, if you want to hear anything about that, just let me know after. Most importantly, okay, I am a wannabe machine learner. Okay, I do not expect anything professional from this. This is actually a hacker's machine learning attempt. Okay, so. As you know, 5 or 6 months ago, I had to do a dissertation. And while many people think, okay, well, that's really boring, which it actually is, I said, let's make something cool. And as I said, at that point, I was really interested in machine learning and AI, generally. And so I said, okay, well, let's get 3 things and stick them together. Okay? So the first one is social media. Okay? Mainly Twitter. Twitter has a really good API for streaming real-time data, and also REST API. So that is a gold mine of information. Second thing is machine learning, obviously. And that we'll be using to get, extract, and classify tweets based on sentiment. And finally, let's put an API on top of that, a scalable API, which will be able to give access to anyone the use of this machine learning as a service. So this is my step-by-step guide to sentiment analysis as a service. So what we'll be talking about here is, obviously, I have to assume you have no knowledge of machine learning or natural language processing. So we're just going to go through a brief overview of what that actually is. And then we'll start looking at the platform, okay, and a couple of very simple steps, which hopefully you'll be able to reproduce. And in any case, I will be releasing these slides. I'm releasing GitHub repository and some really good resources, some really good books, which might help you in building this. And then final thing is, obviously we're speaking about the scientific point of view, but also speaking about scalability and performance. So obviously that is, in the big data world, a big problem. So how can we actually build powerful systems that scale? And this is my attempt at doing it. Probably isn't wrong, but we'll try. So first of all, what is machine learning? Okay, any one of you know what machine learning is? Okay, great, more or less. So this is actually going to be very, very simple, okay, very introductory. So first of all, a little bit of theory, okay. So machine learning is a method of teaching computers to make and improve predictions or behaviors based on some data. So what does that mean? I have a set of data, okay, and I give it to an algorithm. What the algorithm does is it extracts common information. It extracts body from text, okay, or in this case text, so it can be anything. It can be pixels, it can be images, whatever you want. And based on that, okay, based on this data, which can be completely empirical, it can be used to make predictions, understand contours between data. It can do many things. So data can be anything really. It can be stock market prices, so floating point numbers. It can be sensors and motors for like robotics, okay? Or it can also be, for example, text, email, okay? And actually, we'll be using this last one to build the most classic example of machine learning. When someone teaches you machine learning, we start with a spam mail classifier, okay? So this is a very, very simple task. It's actually saying, how can we classify an email as spam, okay, or ham? And so what we do is we start getting body of an email in this case, okay, and let's say we already know that this email, okay, containing these words is spam, okay. So maybe we don't have one of them, we have many, okay, and we have two main labels, spam and ham. This is what constitutes our training set, okay. What a training set is, I don't know, 160,000, 1,600,000 examples of text and a label. We can use a learning algorithm, okay, which here is kind of magic. We're not going to go into too much detail. We're going to see after some code, which is probably going to be more simpler to understand. And this learning algorithm, Merlin the magician in this case, is going to learn the underlying rules between what is spam and what is ham. And what he's going to output is a classifier. And just think of the classifier as a dump of let's say, the result of this learning algorithm, this brain. In this case, it can be a set of weights that combined to the same learning algorithm, okay, can classify. So what we do is, let's say we have another training example. This case, it's not a training example, it's an actual example. We don't know. We want to know, what is this? Earn £300 a week. Let's ask the classifier. Send it through the classifier, and in this case, the learning algorithm, and we're going to get a label. So it's very simple. Train, this is obviously supervised machine learning. Then we have many types of machine learning, unsupervised, reinforcement. But this is supervised. You supervise a learning process on one side, and then you use that information, that knowledge, to classify. Okay, so second thing is natural language processing. Okay, who knows natural language processing? Great. Okay, I get scared now. So natural language processing are a set of, let's say, tools. Okay, please don't hit me if I say something wrong. It's a set. It's a set of tools. Okay. To extract information from text. So natural language is really hard. How can we make computers understand things? How can we make computers extract information from text? And so there's a really, really good library. There's a really good library in Python called NLTK, Natural Language Toolkit. It has some really good features for obviously natural language processing. So we have bigrams or bigrams. Parts of speech, tokenization, stemming, word net lookup, and these are all things we're gonna have a look at. Okay, but what these are functions which can break text into information. And this is just very, very simple example of two simple NLTK features. So the first one is tokenization. Get a phrase, break it up into a word vector. Okay. And while this can be really simple, as the example I'm showing you here, The tokenizer actually does a lot of things under the hood. If, for example, you have sometimes you have punctuation, and so it has many rules to break that up into the best way possible. And then we have stopwords. So what are stopwords? Stopwords are low information words that don't give us any value. Like, for example, if we have the phrase, I wish to buy specified products or service, as you can see, the word to has disappeared. Why? Because it's irrelevant. Okay, it just constitutes noise. Okay. And finally, third topic is sentiment analysis, and this you can assume is a mix of machine learning, supervised machine learning, and natural language processing. And it's the way we can extract information from anything. It could be tweets, text, and based on that, derive a sentiment. So how happy is this person? How sad is this person based on the text? And it turns out the biggest domain is actually Twitter, because it has these streaming APIs, this lots of big flow of data, right? But Twitter sentiment is really hard, actually. I took a long time to find this, but this explains perfectly what I want to mean, okay? So improper language use, so spelling mistakes, picoteur, I don't know, maybe you meant picture, but there's also, you have 160 characters to express your sentiment. That can be sometimes make you do some shortcuts. And finally, different types of English. Even though Twitter API makes you filter by English, there are many types of English, and try to extract text from all these different types can be sometimes very complex. So, after this, we can go back to building our API. So, how do we actually build an API? And we're going to do this starting with a classification. So, classifier. There are three main steps, at least I have identified, of building a classifier, and it starts from the data set. So, as we said, data set is a long set of all your training data, and each training data has text, label. And then we will go through three main processes, and this actually, I wanted to change the name. I will call it the training process. And then finally what we have after the training process is a train classifier. And this change classifier is going to be a file. We can just move that anywhere. So first, a little bit about the data set. The data set I would suggest you to use if you ever wanted to replicate this experiment is Sentiment 140. It's a spin-up project from 3 Stanford University students. And they're actually really good because they have a whole set of information for academia, if you ever wanted to learn more about this. And they give you all the training set, and they have a really good paper explaining their attempt. And they're actually using another algorithm, which is called maximum entropy. But if you ever wanted to get more into this, have a look, not only get the training set, but also look at their papers, because they're really good. And so this training set is made up, this is wrong, it's 1,600,000, sorry. 1,600,000 labeled tweets in CSV, and we have negative, neutral, positive, 3 types of sentiment. And for our example, we're just going to take into consideration negative and positive. And finally, we obviously have the text of the tweet. So first step, feature extraction. So first of all, how would you describe feature? What are features in a phrase? So if you have a point, for example, you could say, what are the features? X, Y coordinates. Really simple. With a phrase, it's really hard to do this. And so what we start with is something called the bag of words approach. And what this actually does is it breaks our phrase into a list of all possible words. And we assume that every word is a feature by default. Okay? This is obviously just a starting point. This is where we start. Second thing, okay, is can you guys see that? Yeah? Okay. So second thing is we build a pipeline of feature extractors. And so what is a feature extractor? It's basically saying there are a set of instructions to manipulate the text, to remove noise from that text, unused features. So I'll just go through a couple of them. So the first one is obviously make lowercase. Very, very simple. Let's make every word lowercase. Remove URLs, hashtags, strip names from, for example, many tweets also have names in them. Remove repetition, that's actually a bit more Twitter related, and you can speak about that after. Then there's some really interesting ones, like for example, remove stopwords, but also stemming, okay? So stemming is getting every word and reducing it to a common stem. And you can obviously understand the benefits of that. If I'm saying walking, walked, it'll remove that to a single root, to a stem. And by doing that, obviously we can group words which are different but have the same significance. And this obviously gives us a big advantage in the learning algorithm. So we do that, and we create this big pipeline. And then what we can actually do is we can wrap this into one main function, which is called feature extractor, .extract. This is a class in this case. We get the body of the tweet, and what we're going to output is the cleaned feature representation, but in a dictionary. And why in a dictionary? And that's just because NLTK, which is the library we're going to be using for the classification process, requires us to use a dictionary. The values are always true, and the keys are our features. Okay, it's just the same as having a list of these, a set of these features. So what we're going to do, just to recap, you get a phrase, split it up into words, features, pass that word down a sanitization pipeline, okay, which is the one I said here. Oops. And finally, you'll get a list at the end of this. Move that to a dictionary. So, feature extraction. Dimensionality reduction. Okay, so we're going to end up with many, many features that are pointless, okay? Like, I don't assume the word elephant or dog, for example, at least maybe me, maybe the algorithm says differently, but there's some words that I assume are not going to consider any information. They're not going to give us anything. And that obviously can be a big problem, because these words are going to constitute noise. They're going to, let's say, make the algorithm less efficient. We're trying to remove everything that is not informative. And so we can try to reduce that dimensionality. And we do this through some very, very simple steps. So first of all, there are actually other benefits from this. Obviously, by reducing all the features, let's say the non-informative features throughout all the classes. Oh, sorry, and one very important definition. Classes are, in this case, what I was referring to previously as labels, and I just forgot to rename them. But basically, in this case, we have two labels, which is positive and negative. And so also by removing noise, we also increase the performance of the actual algorithm, the classifier, but we also decrease the size of the model, so obviously less memory usage and more speed, which is great. And to explain this, actually, I'm not going to go into details of the Chisquare Test, okay, which is a correlation test, and you can actually look it up online. It's very, very simple. But I'm going to speak more about NLTK and how this library has these functions to actually help us a lot. So, as we said, let's go a step back a second. We have one feature set, okay, one feature vector for every training example. What we do there is we get each word and we put it into a set. So we have a unique set of all the words, of all the features, sorry, inside the system. For each word, we just give it a null score at the beginning, okay? Then what we do is we apply this Chisquare Test to each word in the set, okay? So this is going to have all the words from all the training examples, whatever. And we're going to give it a score. The higher the score is, and obviously the more informative the word is going to be. So in this case, for example, the word sad is going to have more information than the word, for example, elephant. And the word sickness, I think, sorry, a bit blunt, is going to have an even higher score. because it probably means more. Okay, the algorithm found out that it means more. And I repeat, I'm not going to go into it. I'm going to show you some code after. It's going to be simpler. But once we get a score for each one of these words, well, what can we do? We could just sort them by score. Okay, so the highest ones are obviously going to be more informative, more relevant. The last one's just going to be noise. And so what we can do is we can, select n, and the n could be anything, and just cut off. So we just say, I want to keep 80,000 features, and that's all entirely up to you. There's no magic number. Keep those, okay, and delete the others. And just to show this a little bit, here is, we'll just go through some of the code, the Chisquare Test code. So what we do is, okay, so what those label word FD are, those are frequency distributions, and those are NLTK related structure. And basically what they just keep is, just think of it as a table of word, how many occurrences has it had, how many times it actually appeared in the system. So here we're saying, okay, how many words are positive, how many words are negative over all the training set. Total number of words, how many words are there in total, and by words here, we're actually speaking about features, obviously. And then we iterate through each word, and we can easily iterate over a frequency distribution, and we have word and frequency, which is the number. And what we do is we calculate a score for each class. So in this case, we have two classes, positive and negative. So we calculate it for the positive side, calculate it for the negative side, and this is just taking into consideration all the information we have before. And this, I repeat, is a correlation, and the way this is implemented is actually very, very simple. You can go and look at the implementation. It's really simple. And finally, what we can do is we have the final score, and the final score is just the sum of all those other scores. So that's how you get this magic number at the end. Then we can go into training aspect. So, oh yeah, sorry, one thing I forgot to say is once we have our cut off set of words, then we have to go back to all the training features we had before and remove any feature that was not present in those most informative words. So for example, let's say the word horrible was in the set, in the most informative feature set, but not the word day. We're just going to remove day. It's noise, just remove that. And we do this for all the training examples. Yeah. Okay, so then once we do that, we've cleaned our training data. So just to recap, okay, the result we have from step 1 and step 2 is a big list of feature vectors, which have already been sanitized, already cleaned, okay, obviously, because we don't have any more we have all the most informative features. And they're also attached to a label, okay, and this label we've been bringing back from the training set, where we have positive and negative. And now we're going to look at a very, very simple algorithm, which is naive Bayes. And this is very, very good, because it's simple, supervised learning algorithm. What's good about this is that mainly there are 3 really good points. Okay? So first of all, it's simple to compute. It's really fast. And the reason, it works really, really well with binary data. And by binary data, I mean this feature is present, this feature is not present. Then there's something called regression, which is basically where you have an actual value, and that value is present, it's not present, it's a floating point, basically. So simple to compute. Assumes feature independence, and this is really important because what this enables us to do is enable us to train it using, for example, parallel algorithms. MapReduce. We can use MapReduce to, in parallel, update our collection, and in case once we finally have our classifier, we can do something called online training, which is basically we can increment the data on top of it without having to restart the whole training process. And for example, there are some algorithms which perform much better than naive Bayes, But unfortunately, they are very, very hard to update. So obviously, I'm favoring here speed and maintainability over the actual efficiency of the algorithm, because if I want to classify, if I have an API, I want things to go fast. I don't want to wait. And finally, it supports multi-class. And this means that up to now, we've considered two main classes, which is positive and negative. But let's say you want to add another class, like neutral. This algorithm allows us to do that. Some algorithms, like support vector machines, which you can go and look at home, can do that, but through a couple of tricks. Like they use something called one-to-many, and there are many different ways of doing it. But anyway, by increasing classes, you also increase the expensiveness, let's say, of the algorithm. Okay? And so naive Bayes is the way to go. And this is very, very simple, let's say, formula of the algorithm. But we're actually going to look at code, because it's far simpler to see. So obviously, NLTK provides these built-in components for us. Training the classifier is really simple. Okay, you import NLTK classifier, an naive Bayes classifier, and it has a class method called train. And sorry, I wanted to actually specify what this train feats is, because by mistake I didn't do that. What train feats is here is going to be our array of tuples of features. It's really hard to explain. Actually, I'm going to show you something after. Far simpler. So just think of this as our training set, okay? And we run the train method, and it says, we're just going to have lots of coffees, lots of showers. It's going to take a bit. And then finally, we're going to come up with a set of labels. So we just said, how many labels are there in the system? Negative, positive. And the cool thing about classification, this naive Bayes algorithm, many other algorithms, is that once you've trained them once, you can just reuse them as many times as you want. So, just serialize them. So train once, use as much as you want. Using the classifier, so once we've trained the classifier, we can actually consume that. And the way we do that is we can just load it using pickle. Okay? So just load the file, get a phrase, and then we have to recompute obviously the step 1 and step 2, okay, and then we classify. So pre-processing, so clean the phrase, okay. Second thing, dimensionality reduction, get that feature vector, and only keep the best features, okay. And then finally, classify. And we're going to get an answer positive in this case. Yeah? So this is good, but this is not going to help us to build our API. To build an API, you have to necessarily have an API process in front of that. And what's wrong with this? There is a problem with this concept of API, sentiment analysis classifier. Well, classifiers are slow. No matter how much optimization you make to them, they're really slow. And it's obviously a blocking process, and API cannot block by definition. And so, what I'm going to propose is an alternative way of doing this. And sorry for the black. I'm going to propose a way in which we can actually scale, okay, horizontally using a library called ZeroMQ. So what is ZeroMQ? ZeroMQ is a really, really good cross-platform library, which is, I wouldn't say it's a wraparound sockets, because it does a bit more than that, obviously. But what it does is it's really, really good to parallelize, okay, parallelize workloads. Just think of it as, let's say, a message queue, but without a main, without brokerless way of sending messages. And so obviously, this makes it really, really powerful for distributed computing in this case. And so it promotes horizontal scalability, language agnostic, and ZeroMQ is really, really simple. What we have here is just an infinite loop, unfortunately, where I receive a message from ZeroMQ, and I do the classification, and then I send it back through the socket. So obviously this is a problem, but if you have many of them, okay, if you have 5, 6, 7, whatever, this can scale, this can scale okay. And if we just go back to this, if you go back to the previous slide, we have ZeroMQ on our API, and ZeroMQ will do something called round-robin load balancing. So it'll basically ask one at a time to each classifier, and it'll keep track to who it asks and the responses it gets. Obviously, all the classifiers just use the same serialized classifier data set. And yeah, so now I'm going to go through a little demo just showing you how simple this is. Okay, so we're going to look at some code. Can you actually see this? No, you don't. Okay, wait. Okay, wait, sorry guys. Can't find. Oh, it appeared over here. Sorry guys. Yay, okay, great. So, let's have a look at oh, damn it, why is that appearing over here? Right, okay, we got it. Can you guys read? Yeah, okay, great. So this is the spin-up classifier. This is the spin-up classifier process. So as I said, it just polls, let's say, infinitely, reads, and sends. Okay, and obviously you can pull these in a supervisor process. And so what I have here is I have I have one serialized classifier running on one process, and this can easily be scaled up to n number. Okay, and then what I'm going to run is a very, very small web application I did to demonstrate this. Well, a bit of time, but it was fun. And what I'm using here is I'm not using a RESTful API, but I'm using WebSockets. So if I search for a term, okay, these worked. Yay. Okay, wait, I don't know why this happens actually. It's terrible. There you go. Okay. So what's happening here? This is communicating with our classifier. Okay. So if I there you go. It's going. It's sending data through the API in real time, and it's receiving classification. And what's cooler, this is, we're using a web application for this, but you can use anything. You can create your own API, and in any language, anything, just using ZeroMQ. Scale horizontally as much as you want. If you have Amazon boxes, for example, you can say, if there's too much workload, then just add another process. And ZeroMQ is automatically going to take that new process under consideration and start load balancing with that too. And this is just a very, very simple example. Just think of the possibilities that can be done with this. That has many, many implications. You can build many different types of systems just with one API. Start with this, build whatever you want. And yeah, so finally, just a small conclusion, okay? So real-time sentiment analysis with Python can be implemented. It can be, up to a certain point, scalable. And as you can see, it sort of works. What's even better is, for example, once I wrote this, I said to myself, instead of using these files, what if we just use something like a distributed data structure database like Redis? What if we use Redis to save our training data? And this is the question I'm asking myself now to re-implement the whole system. So this is just something of my own ideas. And finally, deep learning has given, which is another way, let's say, a completely different branch of machine learning, has given really, really good results. The Stanford NLP deep learning has given really good results in this field. So if you're interested in something new, have a look at what's happening on Stanford NLP deep learning. End.
Thank you. Good news is London seems to be happy now.
Yeah. Sorry about the formatting, the screen formatting.
And I guess lots of questions.
So what's your Twitter handle?
Oh, sorry. Pyros, be free. Do you want to do a real-time tweet? Yeah. Hey guys, let's do a real-time tweet. I won't guarantee this works, okay? Okay, can you tweet with the word PyCon it? You have to. But just in that, it's searching. It's not searching for hashtags. It's actually searching for the word. Okay, please work. Someone tweeted. Yay! But as you see, like, it needs training. But you know, this attached to an API can build anything.
Good.
By the way, my Twitter handle is pyrosbefree, like the GitHub repository. But I'll write that somewhere. All right. Yeah, right. How do I zoom this up? Okay, now Pyros, be free. You can, hopefully you can read it.
Other questions in the meanwhile?
Yeah, sorry.
I have a question about your learning process.
Yes.
I'm not a Twitter, so maybe I missed some point or feature in Twitter. So you are saying you are assuming the mood of people based on the grammatical terms? Words, or there is a feature in Twitter, I am happy and I am sad about it?
Okay, so there is a way of doing this. This is not the way I did it, which is called noisy labels, which is the way, I think that's what you're speaking about. So basically, searching, using the training data, gaining it from, let's say, searching for happy smiles or sad smiles. This is what I did. I used an actual data set, which is on sentiment 140. You can go look that up. And I used that as a training set.
Okay, so sorry, can you repeat
Sure.
the last? It's this set. It's you have a set already prepared.
Yeah.
Okay, and it's based on what? For the mood.
Yes. It's based on the mood of the people, the sentiment.
Yes, but the mood. How you can get the mood? Happy. It's.
There is a guy which already did it for me, and he gave me a training set. Well, yeah, these guys basically...
So it's already prediction?
Yes. They already gave me a training set, okay, saying this phrase, positive sentiment, this phrase, negative sentiment.
Oh, okay.
And I use that to train the system, learn from that,
okay,
and then put it on an API. And so, you know, you can ask, I'm feeling really bad today, and it's going to say, hopefully negative.
Okay. So, bad, negative, happy, people happy, but if you have some ambiguous phrase like my worst enemy is sad, so I am happy.
I can do that through parts of speech tagging.
Okay.
So obviously what I can do is I can break phrases into sentences, find negations, okay? Negate the phrase after.
Okay.
And this is actually something which is inside NLTK. I didn't have time to speak about it. I would have really loved to speak about it. But there are many more things you can actually do.
Okay, thanks.
After, speak to me, I'll give you some information.
I have a question a bit more. Let me say, if you using ZeroMQ, can you use different classifiers?
Yeah.
So to find the sentiment on different products, for example.
Yeah, you can actually, one thing I forgot to speak about is the fact that you can use many different patterns with ZeroMQ. So what I'm using here is something called request reply. I ask, you answer. Okay? You can also use something called push-pull, where basically I push my question, my query to the classifiers in parallel, and they hopefully will answer in parallel, and so you can compare different types of classifiers. So you can also do that. Okay? Obviously, that tends to be less scalable because you're not increasing the scalability by adding more classifiers, because in any case, everyone is going to be pulled.
Hello. So what's the purpose of analyzing sentiments on Twitter? And who uses that, sponsors that kind of research?
Yeah, sorry. So there are many, many uses for sentiment analysis. Okay? Just think of how much information sentiment can give us. Okay? So there are many ethical and non-ethical ways of seeing this. So for example, in the stock market, one of the most famous phrases is, the trend is your friend. Okay? And obviously, in this case, you can use sentiment analysis to sort of predict the ways the stock is going. But you can also use it for example, consumer companies or restaurants do it sometimes. So a restaurant called Quiznos, apparently, which I do not know, in the United States, basically issues automatic vouchers to people which were or really happy or really sad, or had a really bad experience of their restaurant on Twitter. So if I say, Quiznos was terrible today, and I'll have an automatic message saying, hey, here's your voucher. Or just think of if someone has live Twitter streaming on, for example, the World Cup or something. You're obviously, unfortunately, that's never going to be real live streaming, isn't it? You're always going to have someone there which is going to approve or non-approve tweets based on their sentiment. And, you can make a system do that. And that's obviously going to be, that's going to automate it. Finally, also sport events. People use sentiment analysis to predict the way a sport event is going. And so, obviously do like auto-bidding systems. Yeah, I told you, ethical, non-ethical. There's so many ways of doing this. This by itself is not worth that much. It's worth a lot, I think, personally, if we tailor it to something. If we give it a smaller scope. And by the way, I'm going to release all of this open source. So you'll be able to have a look at the repository and play around with it yourself.
One question. Did you also have a look at the big projects in machine learning, like the Mahout library or the Weka library?
I would love to in the next months. I would love to, yeah. Definitely, but from what I understand, Mahout is basically Hadoop with...
Sort of, yeah. They are trying to disconnect it from Hadoop, but, well...
You told me this, I'm going to do it after.
Okay.
Thank you.
So it's not directly relevant to Twitter, but apart from the little detail that Quiznos just went bankrupt, so that may not be, yes.
Too kind.
Chapter 11, maybe too many coupons. Anyway, for data sets where ads can be shown, the importance of sentiment analysis, which nobody had really ever done, 4 or 5 years ago zoomed because there was a strong campaign of consumer advocates attacking a certain retail chain for bad labor practices. So they were mentioning these retail shops over and over in the most negative way possible, as you can imagine. Guess what ads engines tended to show next to those attack articles? Ads for those shops, because they were only seeing these guys mentioning the firm, and that's, hey, it's an article about the firm, let's show ads. The company wasn't too happy having their ads shown about next to an article of how they club baby CEO or whatever they were being accused of doing. So that's when suddenly ad engines say, oh, we really need to do some sentiment analysis so an advertiser can avoid or similar news about big crash on Delta Airlines kills 150 people. Delta Airlines ad showing next to it. Delta isn't too happy. You need sentiment analysis. So ads are just a detail, but there are multi-billion-dollar details. So that's not exactly Twitter. That's more about web stuff. But depending on how Twitter finds to monetize, they might need it.
Okay, I think we have time for one more question. Otherwise, if you want to keep questions going, who needs food? So we can keep here. No question? I think everybody's hungry. So we are breaking for the coffee break now, and talks will come back at 11:30. Thank you guys, and thank you, Pyrathon.
Davvero?